Well, hi there, boys and girls. We are going to look at approximating something called instantaneous rate of change. Now, yesterday we looked at average rate of change between 2 points. Today we're going to try and get a little closer to slope at a single point. And you've never done this before. And that is what a derivative is. Let me go ahead and write that down here. A derivative is going to be a slope at a point, or how to find slope of a graph. And Casey is at the door there, so hold on one second. Well, everybody, Casey says hi. Anyway, so we want to find what is the slope at a point, and to estimate this, we're going to have to make sure we have a good idea of what a tangent line looks like. So that's why I've got this web address up here. We're going to go take a look at a little animation to see what a tangent line looks like, because the slope of a tangent line is going to tell us the slope at that point. We're also going to come back and do some notations for what the derivative is, but let's take a look at what this is. All right, so the thing in white is called a tangent line, and of course it's just attached to 1 point on the graph. And so whenever you're talking about instantaneous rate of change, it's like picking a point on a graph and then imagining a tangent line. That's a line that follows the slope of the curve, but just at that one single point. And we're going to approximate that. Tomorrow we're going to do something actually pretty amazing. We're going to find exactly how to find the slope at a single point by using a limit. But for now we're just approximating. So as we can see, as this white line is traveling through the curve at first over here, it has a positive slope, then it goes negative slope, then zero slope, positive slope. So whenever the white line is tilted down, that's negative slope. And when it flattens out, it's zero. And when the white line is pointed up, that's a positive slope. So that's what I mean by a tangent line. So that's what we're going to be approximating. Let's go back now. Alright, so let's go back here. I'm going to give you some notation for derivative. There's two notations that I want you to write down. One of those notations is f prime of x. We're going to read that f prime of x. Another notation is dy over dx. Both Leibniz and Newton developed two different notations when they were discovering calculus. And this is the notation that we're going to write down to show that we are interested in the slope of the line at that point. Or maybe just in general, how do we find the slope of a curve? And this is also called instantaneous rate of change. All right, so let's get to a specific example. So I've got a function that I've got 1, 2, 3, 4, 5 data points for, and I've got these 5 y values. And what I want to do is I want to estimate f prime at 4.3. That means what would the slope of the tangent line be? At 4.3. Now, the best way to approximate slope of a tangent line is to take a secant line that's really, really close to the point that you're trying to approximate the slope. What I mean by that is take 2 points that are on just right on either side of 4.3 and find the slope between those 2 points, and that will approximate the slope at that point. So this would be, and we've seen this before, what we're going to do is the average rate of change between those 2 points. And these 2 points, notice they're pretty close to 4.3. 3.7 on the left and 4.9 on the right. So this is going to be 2.8 divided by 1.2, which is 28 over 12, which is 14 over 6, which is 7 over 3, which is 2 1/3, which is right there. So we pick 2 points just on either side of where we're trying to find the actual. Keep in mind we're approximating. We're not finding the exact one yet. We're estimating here. Pick 2 points on either side and do what's called a difference quotient, or an average rate of change. I'm going to write that word down because that's pretty important. Difference quotient. This is also the average rate of change formula. Just stay really close to that point. Let's do another example. Let's estimate the velocity. So I've got the position of some object moving along a line. I've got 6-second intervals, and I want to estimate the velocity at t equals 9. Now you need to understand that velocity is the derivative of position. So that means we are trying to approximate, oh well, nice spelling there. Let's try that again. P-O-S-I-T-I-O-N. Yes, there we go. All right, so velocity is the derivative of position, so we are going to approximate the derivative or the slope of the tangent line at t equals 9. So we look at our table, and t equals 9 is, in here. So what are we going to do? We are going to do a difference quotient, or an average rate of change with 2 points that are really, really close to 9. So that would be f of b minus f of a over b minus a, which is -3 over 6, which is -1/2. So that means if we were to draw this graph, our tangent line would be pointing down, and that would be the slope of that tangent line. All right, so let's go take a look at a graph and make sure we understand just this visual. At which of the 5 points shown on the graph is dy dx positive? This means the slope of the tangent line. So imagine that little white line coming through here on this graph. Where would it be at A? Well, at A it would be pointing down, and that would be a negative slope. At B it would be pointing down even steeper. That would be a bigger negative slope. And it looks like at C it's like flattened out, and that would be a slope of 0. This is called a horizontal tangent. Whenever you have a horizontal tangent line, your slope is 0, and that's going to be really important for us in calculus because that allows us to find whenever a curve has maybe a maximum or a minimum. But right here at D, the tangent line would be pointing up, and that would be a positive slope. And out here at E, again, it's flattening out. So this answer would be at D, dy dx is positive. Okay, my table didn't come through here on this next one, but we're going to estimate some slopes, and there is one extra caveat or one extra thing I need to tell you about derivatives. Let's take a look at A, B, and C here. What would the slope of the line be right here at A? Now, in calculus, we call this a sharp turn or a cusp or a teetering tangent line. Is that the tangent line, or is that the tangent line, or is this the tangent line from where? And so this is like a teeter-totter, a teetering tangent line. So we're going to say that at A, f prime of x, I'll make my little table over here, at A, f prime of x would be undefined or does not exist. And the main reason is the slope from the right and the slope from the left don't match at this sharp turn, so you cannot find a derivative there. You can't put a tangent line there that has a unique slope. It'd be, teetering. Now what about down here at B? What would that slope be? So you just draw yourself a little baby tangent line, and that would have a slope of 0 because it's horizontals. I would say it's about 0. Now what about here at C? At C, if I drew a tangent line, that tangent line would have a positive slope, and it's probably bigger than 1. So I would just estimate that it'd probably be something like 4. It's definitely a positive number, right? All right. So that's it. Tomorrow in class, you're going to be approximating instantaneous rates of change, and I will see you guys then.